going to introduce now three different theorems that deal with proportionality in triangles. So we're going to start off with something called the side splitter theorem, right? And so what this theorem is saying is if we're dealing with a triangle and we draw a line segment inside of the triangle that is parallel to any one of the three sides in the triangle. Right, so let's just start off with that part of it. It says if a line is parallel to one side of a triangle. So I'm going to grab my line tool, right, and we're just going to choose to draw this line right here anywhere we want along AB, right, and I'm going to connect it over here and say it's parallel to AC, right, and it's hitting both AB and BC. So this is my parallel side. Remember, we mark parallel sides in triangles or in any shape, anytime we're dealing with parallel lines, just with arrows, right? So I'm marking that these are parallel. So here's what the claim is in this problem. It says if we do that, and this parallel line intersects the other two sides, which we can see that it is, then it's dividing those two sides, which for us is AB and BC, into two proportional sides, right? It's dividing them into proportional parts. So let's add in a couple of new points here. So I'm going to say this is D and E, so we can talk about the line segment. So what this is really saying is that this little segment AD here, okay, if I set that up over, okay, the rest of the segment DB, right? If I set up this fraction, that they're claiming that it will be equal to if I did the same thing on the other side. So I'm going to say EC, this little piece over here, right? This was the little segment AD on top, so I'm going to do the same thing over here, EC, over the other bigger segment of BC. So we actually split these two big segments into smaller segments, and the claim here is that we're going to create two equal proportions, right? And so if you think back, we had the mid-segment theorem back when we did triangles a while ago, and the only minor difference between this theorem and the mid-segment theorem is we assumed that the sides here are being bisected, right? So if we were kind of looking more at a picture that looks something like this, where the parallel side was way over here, and maybe it was cutting that segment into equal pieces. And if you notice, if I were to set up equal pieces in a proportion, that would be true as well, right? If, for example, if AD and DB were equal, and EC and EB were equal, I would end up also getting a proportion. So this side splitter theorem is actually just a very much more general version of what you learned about when we talked about mid-segments, right? So the rule about the mid-segments creating equal part works as well, because the mid-segment being parallel, it was also creating a true proportion, right? So just keep in mind that this is kind of an application of that mid-segment theorem. So let's take a look at some examples of just this theorem happening. So because I'm seeing in my problem here, problem number one, that the line KL is parallel to the line PN, this side splitter theorem is claiming that if I set up the two segments that were created on the left-hand side of PM, right, 12 over x plus 1, that should be equal to the segments that were created on the other side in a fraction, right? This proportion is true. So if I multiply 12 times x, I get 12x. If I multiply 9 times x plus 1, I get 9x plus 9. Remember, this is a distributed 9, okay? And if I solve this, I get, subtracting 9 on both sides, I get 3x equals 9. Right, and I can say that x is equal to 3, right? So that's an example for you. If you want to try out the one on the right, it's pretty much the same thing. It's going to be the same type of setup and solve, so I'm not going to do the second one as well, right? So we can actually take this idea of the side splitter theorem and parallel lines creating proportional parts, and we can extend it a little bit more. So here's what it's called a corollary to that side splitter theorem. So what a corollary is, if you remember, is we're saying, let's kind of say, because the theorem is true, there are some other things that are true as well, and they're kind of just kind of an obvious statement. So what this is saying is if maybe we don't necessarily have a triangle, but we just have three or more parallel lines, then we're actually going to get that proportionality happening for the segments that are created when we draw in transversals. So again, here are my three parallel lines, right? So I just pre-drew them. So I'm going to say these three lines are parallel, okay? And I drew in two transversals, just like the two sides of a triangle. So what they're claiming is that if I had a number here, which I'll call x, and I had a number here, which I'll call y, and I had a number here, which I'll call a, and a number here, which I'll call b. I'm able to measure like the line segments that are showing up in between these parallel lines. Then, just like in the triangle, that the two segments on the left here, x over y, will be equal to the two segments on the right here in a fraction, right? They are proportional when we set it up. And this is true for any type of problem. So this is actually really helpful because, for example, if you kind of focus on the inside of this picture, right, without all the extra lines, this right here, okay, is actually a trapezoid. Right, so this idea of the side splitter theorem will apply to any types of shapes that we draw that have two parallel lines, three parallel lines, and a transversal. So we can apply this to not just triangles, but to a lot more shapes as well. So let's just take a look at one quick example of this happening. Right, so we have our campsite here, right, and the campsite, we know that they divided the campsites using parallel lines, right? So these lines here that are doing the splitting, right, are parallel lines. So I have this one, right, cutting the campsites into equal pieces. And in this case, they use 4 parallel lines, right? Okay, pretending like I can draw straight lines here, okay? All right, so if I take a look at the other sides, I'm saying there's this bottom side here, right, this big one going across, right? And then there's the coastline, right, which we care about as well because we can measure some of those things. So they didn't measure everything. What they actually did was they only measured the coastline of the two site B and C, and they only measured the kind of the road line of site A and B. So here's what the claim is. If we kind of forget about, I'm going to cover it up so we don't see it. If we forget about one of the sites and just look at the other two, right, we're actually going to be able to set up a true proportion. So I'm just going to cover up site C for a second and say, let's make this one go away. If I just focus on this, I have that situation. Here's 3 parallel lines and 2 segments that got cut into pieces. They're claiming that if I set up the bottom ones, right, the 9 and the 7.2, if I set that up in a fraction, 9 over 7.2, that it should be equal to, if I call this missing side, where it's saying what is the length of the site A along the river, right, if I call that x, because it's unknown, I can set this up as well. We're saying 9 over 7.2 equals x over 8. So if you notice how this is set up, the 9 is from site A, and the x is also from from site A. So I'm trying to keep those parts together. So I can solve this one. I can cross multiply 7.2 x if I multiply the two extreme values, I'm sorry, the two mean values, and if I multiply the two extreme values, I get 72, right? And if I divide both sides by 7.2, I get that x is equal to 10, which means that this little segment of the coastline has to be 10 yards long, right? I can do the same thing, and I'm not going to go through it because it'd be repetitive, and I can say, you know what, let's forget about site A. So if I move this over here and just say, let's forget about this now, right? And I can do the same thing over here, and I can just put my x, if I want, down bottom here, and set up another true relationship. Use the 8 and the 6.4 in a fraction, and use the 7.2 and the x in a fraction, and I'll be able to figure out what site C is as well. So as long as I know about one of the little segments, one of those little sections, I can actually do this for an unlimited quantity of parallel lines. All right, so we have one more problem that we're going to take a look at, and this is called the triangle angle bisector theorem, which is a lot more words than it is difficult to do. So what this is claiming is that if I draw a ray in any triangle, and that ray is a bisector, then we're going to end up with proportional parts looking at all of the other segments that are in the triangle. So I, again, pre-drew my picture. The orange line is an angle bisector, so that means that I know that these two angles at the top are equal to each other. So here's what the claim is for the triangle angle bisector theorem. Again, I'll just use some letters to label my sides. I'm going to call this one A, and I'm going to call this one B. Right, and then down here, the third side, the one where the angle got bisected, got split into parts. Be careful, these parts are not necessarily equal to each other, even if the picture might look like it. So I'm just going to call these C and D. Right, I don't necessarily know how long they are, but I know that the big line got split into 2 smaller segments. So the claim here is that if I were to take, and there's a couple different ways that we can set this up. If I were to set up, like for example, the 2 segments on the bottom, C over D, okay, then I could set this up in a fraction with A over B, right? So I'm saying the 2 little segments that I created over the 2 other sides, that this is a proportional relationship. So the way I set this one up, if you notice, if I were to write in words the way I set them up, this is out of both of these A and B, or A and C sections are out of the left-hand triangle, right, the little left-hand one that we created, and the D and the B are out of the right-hand triangle. So I was consistent in how I set up my parts. I used the 2 small segments on the top and the 2 longer segments, I used the 2 smaller segments in the first fraction and the 2 longer segments in the second fraction, and then when I go across the top, I was also consistent. I used the ones from the left-hand triangle and the right-hand triangle. So if I wanted to, I could write this in a different way, and I could say, let's set up the 2 ones in the left-hand triangle, right? I could also write this as A over C, right? The left-hand triangle's parts equals the right-hand triangle's part. So kind of whatever clicks to you. If you take a look across at A and B, these are now both long sides, right? The unbroken sides, we'll say, and the ones on the bottom are the short sides, or the ones that we split by using the bisector. So this is two different ways that I can write this situation, but the big idea is that any way that we write it, we're getting proportional parts, right? So again, let's take a look at one quick example of this happening, right? If I take a look at a picture like this, they didn't really say anything. It's just solve for x, right? So we really need to take a look at this and say, right here at angle P, I'm getting that bisecting happening. So I know that at the very least, we have proportional parts. So I'm going to choose to set up the two sides of the left-hand triangle, the 10 and the 12, in a fraction. Okay. And I'm going to do the same thing on the right-hand side. So because the 10 was from the segment part, I'm going to use the 18 on the top as well, because that's also from the segment of RS. And then I don't happen to know the long side PS, right? So I'm going to set this up. So this is 10x, right? 10 times x is 10x, right? And then 18 times 12, okay, is 216, okay? So I'm going to say that if I divide both sides by 10 here, I get that this side, length of PS, is got to be equal to 21.6. Okay? So you can see that proportionality shows up in a lot of different places. This is 3 different theorems that we can apply to triangles and in some cases to other shapes to use proportionality to find missing parts.